Good morning, pre-calculus. Over the course of the next couple of live streams, got a lot of ground that I want to cover, and the topics are going to be two very different topics. So here we are in the last half of our semester. We've got an understanding of linear functions under our belt. We have an understanding of quadratic functions under our belt, their properties, how we can use them to model different types of behavior, and so forth. And so we really have two more function models that we need to wrap our heads around before our course is over. The first one is the one we're going to spend most of our time in today's live stream talking about, and those are called the rational functions. Rational not necessarily in the way that they make sense and they use logic, although they do, but rational inspired from the mathematical concept of a rational number. A rational number is the result of taking an integer and dividing it by a non-zero integer. And when I divide an integer by a non-zero integer, I get a fraction, which sometimes evaluates to a whole number, but very often does not evaluate to a whole number. And we call that set of fractions the rational numbers. Rational numbers are anything I can write as the quotient of dividing an integer by a non-zero integer. So in the same way, a rational function will be the result of dividing one whole type of function by another non-zero whole type of function. I have a numerator, I have a denominator, and both the numerator and the denominator of a rational function are whole functions in the sense that they are polynomial functions. So now that we know what polynomials are, we have an understanding of how they operate. Rational functions is the answer to the question, what happens when I divide one polynomial by another polynomial? Because that's the only operation we can do to polynomials that doesn't necessarily give us back another polynomial. I can add a polynomial plus a polynomial, and the result is a polynomial. I can subtract polynomial minus polynomial and get a polynomial. I can even multiply polynomial times polynomial, and the result is always going to be a polynomial. But division is a different story altogether. When I divide a polynomial by a polynomial, I do not in general get a polynomial. What I get is called a rational function. And so today is going to be all about studying the rational functions, the class of rational functions. What is their types of behavior? How do we understand their graphs? How do we play the same game and ask the same questions about them that we asked about polynomials in our previous live stream? So rational functions is really our main point of focus for today, but because we're going to do two live streams kind of in rapid succession, I kind of want to also introduce the last type of function we're going to talk about this semester in pre-calculus, which are the exponential functions. So just as a quick overview of the next two live streams, what are we going to be talking about? First of all, for rational functions, there are three main questions we want to be able to ask and answer about rational functions. The first is about domain. Anytime we are talking about any type of function, the first question that we want to answer is what kinds of x values, what kinds of inputs can we put into my function in order to get an output? So what x values are valid, give us valid outputs from our function. That's called the domain, and it's a much more interesting question for rational functions than it is for really any other type of function that we've studied so far, because not every x value will give us an output. And the key to understanding how to find the domain of a rational function is going to be to use factoring methods, and we'll see why that is in a few minutes. Factoring is also going to be necessary for us to understand the local behaviors of a rational function. So what happens to the outputs of my function for values of the inputs that are very nearby one of these x values that we've had to exclude from our domain. So once we figure out how to exclude x values because they're not a part of the domain of my function, the question then is, well, how does this function behave locally if we zoom in on that x value that we took away? What's really happening to this function near that excluded x value? And there's kind of two different types of behavior. One of them that we're seeing on this graph here is called a vertical asymptote. This is what happens when the graph of my function approaches this vertical line on my Cartesian coordinate system, but never actually crosses that vertical line. It approaches it infinitely closely, but it doesn't actually cross this line. A sort of galaxy brain sophisticated mathematician might say, well, it does cross this line, but it crosses it at infinity. So we're going to use the concept of infinity once again today to talk about what the behavior of a rational function near one of its vertical asymptotes looks like, and how do we discover it from the algebra and not just from a picture of the graph. But the second type of local behavior that we'll study near an excluded value of the domain of a rational function is called a removable discontinuity, also known as a hole in the graph. So local behaviors near excluded values fall into one of these two camps. We have the vertical asymptotes, as we're seeing at these two excluded values, but we also have excluded values that don't result in vertical asymptotes. They result in infinitesimally small gaps in the graph, places where we have to lift up our pencil ever so briefly as we're sketching the graph, but then we put it right back down immediately afterwards. Mathematicians call these removable discontinuities, because if we were to fill in this hole on the graph, it would completely fill in a continuous curve shape at that point. But as a matter of what the local behavior of that function actually is near the point, that value of x has to have been taken away. So two types of local behavior, vertical asymptotes and holes. And just like for the domain, we're really going to need to understand the factored form of our rational functions expression in order to classify local behavior. We're also going to use a strategy called a sign chart to be able to tell apart the different types of vertical asymptotes. This vertical asymptote looks like it has a different local behavior than this one does. At this vertical asymptote, my function is approaching different signed infinities on different sides of my vertical asymptote. Whereas at this vertical asymptote, we have some agreement that my function is approaching negative infinity from both sides. So we'll use a sign chart to differentiate those types of local behavior at vertical asymptotes. And then finally, just like we asked for polynomials, what is the end behavior of a rational function? End behavior has more to do with, as always, what happens as the value of x goes all the way out to the right towards positive infinity, or all the way out to the left towards negative infinity. How do we understand what the values of f of x are really doing? And with rational functions, it's a much more rich universe of possibilities than it was for polynomials, because we can still have our function approach positive infinity or approach negative infinity as we go out towards the right and left horizons of my graph paper. But there's a third, actually 4 different options. We're going to include 2 new ones. One of them is one that we're seeing here called a horizontal asymptote. That is a horizontal line in my Cartesian coordinate system that eventually, if we zoom out far enough on my graph and we blur our vision to all the local behavior that's happening in between, we would see that this graph pretty much looks like a horizontal line. And that horizontal line has an equation that we call its horizontal asymptote of this graph. The fourth possibility is a possibility we call slant asymptotes. A slant asymptote is a line that my graph looks like if we zoom far enough out, but it's not necessarily a horizontal line. It would be a line that has some positive or some negative slope. So how do we discover horizontal and slant asymptotes to classify the end behavior of a rational function using the algebra, using the formula for that function, and not just by looking at and trusting a graph? Right? So that's the agenda for today's segment on rational functions. Let me just give you a quick preview of what we're going to talk about in tomorrow's live stream about exponential functions. Exponential functions are our last function type for the semester. And just like with linear functions, because we have a brand new type of arithmetic at the table, a new type of equation model, we want to understand first how to spot exponential behavior. What kinds of measured phenomena lend themselves well to being modeled by exponential functions? And it has to do with a relationship between added quantities in the independent variable, so additions in my x variable, let's say every time I add 1 to my x variable, we see a consistent thing happening in the y variable, except that that consistent thing, unlike linear functions where the additive changes have to be consistent, for exponential functions, it's a multiplication that is consistent. Every time we add 1 to x, we're multiplying y by a consistent amount, and that amount is called the base of your exponential function. Base for exponential functions is going to have the role that slope had for linear functions. So when we change up the type of arithmetic and go from linear to exponential, we also change the main characterizing parameter of my behavior from slope, which is what we called it for linear functions, to base, which is what we call it for exponential functions. And then we'll also talk tomorrow about a special number, a special irrational number called e. Where does e come from? Why is it interesting for us? It's kind of a hard story for us to tell in pre-calculus, so we're going to tell it through applications, actually. And it's not until calculus that we really start to put onto a firm foundation why the number e is so interesting and important. So next semester, your appreciation of the number e should be perfected in some way. We're just going to give you an introduction to it as part of tomorrow's live stream introducing exponential functions. So if you're watching us live today on Twitch and you're not one of my current students, feel free to drop any questions that you might have about today's exposition and lesson into the Twitch chat. And if you're one of my current students and watching this live today, welcome. It's good to see you again. Feel free to drop any questions that you might have about today's lesson into our Slack class discussion channel. I'll prioritize your questions over the questions of anybody that might ask from outside of class for today. So, where do we begin in our study of rational functions? So what I want to do is actually start with this graph that I sketched. And this graph is sketched so as to illustrate all of the interesting salient features of a rational function that we might care about. And so that graph is going to be where I begin. And I came up with this graph just by coming up with a rational function. And as I was saying in our introduction, what characterizes and defines rational functions is that their formulas are obtained by taking one polynomial and dividing it by another polynomial. So fundamentally, rational functions are about division. They're the result of a division problem. And the numerator and denominator of this division problem are each polynomials. So they're sums and differences of monomial terms. So what we get when we divide one polynomial by another polynomial. And one of the more important features of any polynomial, and we're going to keep track of this right here at the outset, because it's going to help us to classify the end behavior of rational functions, is the degree. The degree of a polynomial function tells us a lot about that polynomial function's behavior. And in this particular example, for this formula that gave me the graph of this rational function, the degree of my numerator is the degree of its highest order term. That's x to the fourth term, so that degree is 4. Same thing with my denominator. It's also a polynomial of degree 4. As you might expect, not every rational function is going to be made up of dividing a polynomial by another polynomial whose degrees are equal to one another. When those degrees are unequal, we still have a rational function. But that inequality in the degrees actually gives us different types of behavior as far as the end behavior of my rational function goes. So comparing the degrees, contrasting the degrees of numerator and denominator, turns out to be an important thing for us to do in a moment. So for right now, I'm just going to note it. The degrees are 4 in the numerator and 4 in the denominator. So what are we going to be able to do with this rational function without putting it into its factored form? Well, the good news is that we can do something. What we can do with this rational function before putting it into its factored form is we can understand its end behavior. Without factoring, we're going to be able to zoom out on our graph and figure out what's really going on here at the end of the day. Let me switch over into my browser window that has a nice graph of our rational function to play with here. So here's our rational function that we're playing with. And let's imagine that we just want to zoom out on this graph as far out as we can possibly go. So we don't care about what's happening at little values of x like 1, 2, or 3. We care about the big picture as x's go all the way out to plus infinity, all the way out to minus infinity. What does this look like? So today, instead of using Desmos, I'm using the GeoGebra online system. It can pretty much do the same thing, but I like how it shows us formulas a little bit nicer. So I'm going to zoom out on this graph. Not just a little bit, but a lot. Zoom, 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 zoom. As much as possible. Keep going, keep going, keep going, keep going, keep going. And the further out that I zoom on this graph, I'm going to turn my axes off here for a second. I'm noticing on this graph a couple of things. On the one hand, I've got this sort of vertical line shape thing going on. And because it's a vertical line, that really has more to do with local behavior than it does have to do with end behavior. And we're going to get to local behavior. It's a much more complicated picture than end behavior. So I'm going to just not care about that vertical line for right now. What I care about instead for end behavior is this horizontal line that I'm observing here in my graph. And horizontal lines, remember, have equations that look like y equals a constant. So let's think for a moment about what y equals a constant is going to look like as an equation for a horizontal line. So if I take, I don't know, y equals 10 or something like that, that gives me an equation that looks an awful lot like a horizontal line, and that horizontal line is placed at 10 on the y-axis. Well, it doesn't seem like that's the horizontal line that this graph most resembles, so we'll try some other ones. What about y equals 0? That's the x-axis. It doesn't look like y equals 0 quite hits the mark either. If I zoom myself back in, it looks like this y equals 0 line that I just placed on my graph doesn't well sort of model the behavior that I'm seeing in this graph as I scroll all the way out to x equals minus infinity, or as I scroll all the way to the right towards x equals positive infinity. So what I really kind of want to do here is I want to tune my my horizontal intercept however I can, to try and get the y value of that intercept to match up with what we want here. And for some reason, GeoGebra is being stubborn about letting me do that. There we go. So as I change the y value of my horizontal line, what I want to find the one that my function approaches but never actually crosses. So if I take I don't know, y equals 1.3 or something like that, it doesn't look like I cross y equals 1.3 as x goes to positive infinity, but as x goes to minus infinity, take a look, there's a point right here where my graph crosses and falls below that y value for the rest of time. So 1.3 doesn't seem right. I want to adjust it a little bit down. What about 0.9? Well, 0.9 as a horizontal line never gets crossed as x goes to negative infinity, but apparently it does get crossed as x goes to positive infinity. I've got to zoom in a little bit to see. But sure enough, it looks like my graph does, in fact, cross that line and remain above it for the rest of time. So it turns out for this rational function, the horizontal line that best explains this end behavior as x goes to plus and minus infinity is the horizontal line y equals 1. So that's the horizontal line that if I zoom far enough out on my graph, that's what this rational function eventually looks like. So if I go way out, x equals minus 1,000 to 1,000 or something like that, that horizontal line, y equals 1, is what my graph looks like. So y equals 1 is what we're going to call the horizontal asymptote of my rational function. So coming back to my whiteboard right here, the way that we say it using the arrow notation that we talked about when we talked about end behavior for polynomials is we'll say that as x approaches positive infinity or as x approaches negative infinity, f of x approaches the y value of this horizontal line. Now, how could we have known that that y value is y equals 1, as I'm claiming? Well, here's the key to finding end behavior of rational functions using algebra rather than using and trusting a graph. Just like with polynomials, the larger that x gets towards a positive infinity or towards negative infinity, the more that the polynomials which define the formula for my function f of x will follow their leader. And by their leader, I mean their leading terms. So just like we did with polynomials, to understand the end behavior of rational functions, what we want to do is look only at the leading terms of the polynomials that are in the numerator and that are in the denominator. So let's take a closer look at what that would look like in this example. So what I want to do is I want to throw away everything in my numerator and everything in my denominator except for the leading terms of those respective polynomials. The leading terms are the terms that give us the highest degree. And so in this example, those leading terms in the numerator are x to the fourth, so I'll ignore everything else. And in the denominator also x to the fourth. So I'm just going to sort of erase every other term except for the leading term in the numerator and the denominator. And what's great about that is that once I've erased everything but the leading terms, then what I have left is no longer a polynomial, but it's now just a monomial. And when it's a monomial, that means that we're going to be able to do some algebra to simplify and better understand what we have here. So what we're saying is that as x goes out to plus and minus infinity, if we squint really hard and zoom way out on my graph, these leading terms are calling all the shots, and the value of f of x is basically, within the small order of magnitude, just equal to the ratio of the leading terms. But when I take x to the fourth and I divide it by x to the fourth, algebraically, as long as x is not equal to 0, and the further out towards the infinities that we get, we know for sure that x is not going to equal 0, that quotient is just equal to 1. And that number 1 is what tells me the location of my horizontal asymptote. Because as x goes out to plus infinity, or as x goes out to minus infinity, the value that the number 1 takes is that it just stays the same, right? It's this number 1 here is a constant, and so it doesn't care what x is doing. So as x goes out to plus infinity or minus infinity, the number 1 remains the number 1. And that number 1 tells me the equation of my horizontal asymptote for this rational function. The equation is y equals 1, just like we expected from the horizontal line that we were sort of moving around on the GeoGebra window just a minute ago. Right? So a rational function will have a horizontal asymptote when this end behavior stabilizes on a constant number, a non-zero, a finite number. Right? And so that happened in this example because the ratio of the leading terms, x to the fourth divided by x to the fourth, turned out to be just a constant, just the number 1, which as x goes to infinity, just remains the number 1. So for the sake of contrast, what would have happened if we had different types of behavior? What if our leading terms were different? If they didn't have the same, if they didn't cancel out to a constant as nicely as they did in this example? So what would we have to do differently in a different situation? I want to cover this real quickly because hopefully, if you're watching this carefully, you're already sort of wondering what the case would be. What are sort of the different things that could happen in these examples? So here I have just a couple of other examples of ratios of leading terms just to talk about. So these would be from different rational functions, not from the one we're looking at here. In this example for g of x, I have 3x squared as the leading term in my numerator and x to the third as the leading term in my denominator. Then for h of x, I've got minus x to the fifth as the leading term in my numerator and 3x to the fourth as a leading term in my denominator. So what would have happened in these different scenarios? Let's look at g of x first. If these are my leading terms, and I simplified this ratio of monomials, 3x squared divided by x to the third, well, that would give me 3 over x, wouldn't it? Because I would have 2 minus 3, or negative 1, powers of x in total. So my x to the 1 would end up in the denominator. And then the question is, what happens to 3 divided by x as x approaches infinity? This is like saying that I have 3 pizzas that I want to divide up, and I have x friends coming over to eat pizza, and so each one of my friends is going to get 3 over x amount of number of pizzas to eat. Right? But as x goes to infinity, I have infinitely many more friends coming in the door, but I still have only my 3 pizzas left. And so the more friends that come in the door, the less pizza each one of them is going to get, because there's only a finite amount of pizza to go around. And so the larger that x gets, the smaller that 3 over x gets, and in the limit, as x goes to positive infinity, the amount of pizza that each of my friends gets goes all the way down to 0. So as x goes to positive infinity, the value of 3 over x goes to 0. And so that example would be an example in which we would have a horizontal asymptote once again, except instead of the horizontal asymptote being placed at y equals 1, here the horizontal asymptote would be placed at y equals 0. In other words, here the horizontal asymptote would be the x-axis, whose equation is y equals 0. How could we have known that that's what would happen in this example? Or maybe the better question is, what's the giveaway? What's the clue without doing all of the limit work here? What's the clue that the x-axis, or the y-axis, would be my horizontal asymptote? Well, this happened because we ended up with a power of x in the denominator, but no power of x in the numerator. So any time that we have more x's downstairs than upstairs, when I have a higher degree for my polynomial in the denominator than I had in my numerator, this is going to happen every single time. Because all of the x's that are left over in the denominator, as those go to infinity, we have a fixed amount of pizza to go around to that infinitely many number of friends, because I had more x's downstairs than upstairs. So anytime the denominator has a higher degree than the numerator in a rational function, it will have a horizontal asymptote that is the x-axis, the equation y equals 0. Our second example here does the opposite, right? My numerator has a higher degree than my denominator. What's going to happen in this example? When I simplify this ratio of monomials, the result is negative 1/3 times x. Or another way to say that is it's minus x over 3. I have more x's upstairs than I had downstairs. So what's going to happen here? Now, the amount of pizzas that I have is getting bigger and bigger and bigger. So the delivery person keeps coming through the door and giving me more and more and more pizza. But I only have my 3 friends sitting on the couch, ready to eat. So how much pizza is each one of them going to get? Well, my amount of pizza is becoming infinite, but my number of friends is staying the same. And so the more pizza that comes in, the more that each of my friends is going to have to eat. And so that ratio, x over 3, as x goes to infinity, is going to grow without bound and become infinite. And because we had this negative sign sitting out in front, the type of infinity, that we're going to get is we're going to get a negative infinity out of this. So as x goes to positive infinity, this h of x, this rational function, which is governed by this ratio of leading terms, is going to approach negative infinity. And so in that example, as x goes to positive infinity, as we go further toward the right on my graph, the y values are going down and down and down and down and down without bound. And so my graph is falling through the floor as we go toward the right, towards x equals positive infinity. And so in that example, we do not get a horizontal asymptote for this function as x approaches positive infinity or minus infinity. And so that happened because my numerator had a higher degree than my denominator. So the three examples that we're looking at here classify the three different types of end behavior that a rational function can have. When the degrees of numerator and denominator are equal, as they were in our original example, we get a horizontal asymptote. And that horizontal asymptote is not the x-axis. It's some other horizontal line. In this case, it's y equals 1. When the degree of the denominator is higher than the numerator, we also get a horizontal asymptote, but this time the horizontal asymptote is y equals 0. In other words, it's the x-axis. And finally, when the degree in the numerator is higher than the degree in the denominator, we do not get a horizontal asymptote at all, because as we zoom out, the end behavior looks like the end behavior of a polynomial function of a positive degree, which is that that polynomial function is either going to go to plus infinity by crashing through the ceiling, or it's going to go to minus infinity by crashing through the floor. Those are the three different types of end behavior that we can get for a rational function. And whether or not the degrees of the numerator and denominator, how they compare, which one is larger than the other, or whether they are equal, that is what classifies the end behavior for rational functions. So in our example, the end behavior is that we have a horizontal asymptote, and that horizontal asymptote is y equals 1. So that's the story for end behavior. End behavior is governed entirely by the leading terms of our numerator and our denominator. And the leading terms of numerator and denominator are something that we can tell without having to factor. And that's always a good thing, because factoring is the hardest thing that we can do in algebra. So where do we go from here? Well, to determine any other type of behavior, any other salient feature of a rational function, other than the end behavior, we're going to need to have a factored form for it. And the other types of behaviors that we care about are the local behaviors, not the end behavior that we get by zooming out, but the local behavior that we can get by zooming in near an x value. And the first question is, what x values are interesting? What x values do we care about for the local behavior of a rational function? And the first part of the behavior that we're going to care about for local behavior is just what x values are even possible. What x values can I even put into my function f and get a value out at the end of it? We're going to need factoring to learn that answer to that question, and that answer to the question is the answer of the domain question. What is the domain of my rational function? Finding the domain of a rational function is all about, on the graph, remember, taking my graph and just trying to squish the graph down onto the x-axis to figure out which portions of the x-axis this graph actually covers. For this particular example, when I squish my graph onto the x-axis, I find out that it covers the entirety of the x-axis with exactly 3 exceptions. There's an exception at each of these vertical asymptotes, because for these x values, there is no point on my graph to give me a y value. No point on the graph above or below this x value either. And there's also no point on my graph that's above this x value or below this x value, because immediately above it, we have this teeny tiny little gap in the graph that we're going to call a removable discontinuity. So there's 3 x values that we have to throw away from the real numbers in order to discover the domain of this rational function. So how are we going to figure out what x values to throw away? We call those the excluded values in the domain of a rational function. Why do we need to exclude values from a rational function? Let's go over and look at the algebraic form of my rational function. It's a polynomial divided by a polynomial. And so anytime you're asking a domain question, you ask yourself the question, well, what could possibly go wrong? If I'm trying to evaluate this function, what snag could I run into in the evaluation of x to the 4th minus 2x to the 3rd minus 13x squared plus 14x plus 24 divided by x to the 4th minus x to the 3rd minus 15x squared plus 9x plus 54? What could possibly go wrong? Well, there's only one thing that can go wrong in this combination of arithmetic, because all this arithmetic is it's predicated on addition, subtraction, multiplication, and division, and exponentiation, which, because my exponents are positive integers, that's just multiplication, repeated multiplication of a number by itself. So it's just addition, subtraction, multiplication, division. What can go wrong? One thing: division by 0. That is the only thing that can go wrong if all that we're doing is adding, subtracting, multiplying, and dividing real numbers. The only thing we cannot do, the only arithmetic that is impossible, is a division by 0. So we have to exclude values from the domain of a rational function only because we are trying to divide by a quantity which becomes 0 for some value of x. So we need factoring to understand the domain of a rational function, because we need to know which values of x to exclude. Those are the values that make the denominator of my rational function equal to 0. I'm going to step back here for a moment, and we're going to go through just a simpler example of how to find the excluded values in a rational function. That's just coming from my old Math 095 intermediate algebra videos. So we're going to watch this little one together, and then we'll come back and apply it to the example that we're doing right now. At this point, I wonder if we would mind if I sped up the exposition just a little bit. This is about a 6-minute video, and I feel like we get just as much out of it if we watch it at 1.5 speed. Maybe that's just my jackrabbit brain talking, but let's speed this up just a little bit, and we'll watch the rest of it. Let's get back into a rational expression is done because we want to make sure that the denominator is not permitted to equal 0. So the entire question of finding the excluded values of this rational expression is going to turn on us finding where this denominator, x squared plus 7x minus 18, becomes 0. Any value of x for which that happens must be excluded from the possible values of x at which we can evaluate this rational expression. Notice also that the question of excluded values has only to do with where the denominator becomes 0, and has nothing to do with any properties of the numerator of this rational expression. So in the actual work that we do, the x squared plus 7x minus 18 in the denominator is something that we'll work with, but the 3x minus 1 in the numerator is not relevant at all to our decision making in finding excluded values. So we can ignore the numerator and focus completely on the denominator. So now that we know what the job is, to find those values which make the denominator 0, that tells us that we should set up an equation where the denominator is set equal to 0, so x squared plus 7x minus 18 is equal to 0, and any x which solves that equation will be an x that we need to exclude from the domain of this expression. That means that all we have to do now is to solve this equation for x. Since this equation happens to be a quadratic equation, with a quadratic trinomial on the left-hand side and 0 on the right-hand side, the most efficient method of solution is probably to factor, and then to split each of those factors into its own equation. We can factor x squared plus 7x minus 18 using the sum and product method to find a pair of integers which multiply to give us negative 18 and which add to give us positive 7. Such a pair of integers are positive 9 and negative 2.
So we can factor the left-hand side as the product of x plus 9 and x minus 2. Since the right-hand side of this equation is 0, having factored the left-hand side means we can split it apart into two pieces. One equation, x plus 9 equals 0, and another equation, x minus 2 is equal to 0. Solving each of these simpler equations will give us the values of x that we're looking for. We can solve the first by subtracting 9 from both sides to get x equals negative 9, and we can solve the second by adding 2 to both sides to get x equals positive 2. Each of these values, x equals negative 9 and x equals 2, makes the expression x squared plus 7x minus 18 equal to 0. And therefore, if we were to plug either of these values of x back into our original rational expression, the result would be a fraction whose denominator is equal to 0, and therefore whose value is undefined. Therefore, these are exactly the values that we must exclude from consideration in the domain of this expression. So finding the excluded values of a rational expression means finding those values of x, or whatever its variable happens to be, for which if we were to plug those values into the expression, the result would be an undefined fraction. And this will happen exactly when the denominator of that fraction is equal to 0. So finding the excluded values is simply a process of setting the denominator of this rational expression equal to 0, and then using whatever method is appropriate, solving that equation for x. Rational expressions.
So what do we take away from that? To find the domain of a rational function is to find the values of x that we must exclude from consideration because they make the denominator equal to 0. So bringing that home to the example that we're working with here, if I want to know what the domain of this rational function is, I need to know what values of x make x to the fourth minus x to the third minus 15x squared plus 9x plus 54 equal to 0. So I have to solve a polynomial equation, which is something that in general is a very hard problem to do without technology, right? So because I chose this example that we're working through today to have all the different features that we want to study, I had to choose an example that was somewhat complicated, right? A fourth degree polynomial in the denominator. So I hope you'll forgive me for saying we're just going to factor this using technology. So I went and I opened up a computer algebra system and I said, tell me what the factors of this polynomial are. I don't expect you to factor fourth order polynomials that simply, though you could with synthetic division. You could take some guesses as to what the roots were and then use synthetic division to break it all apart. But when we do that factorization, here is what we end up with. So we end up getting these three different factors: x plus 3, x plus 2, and a second power of x minus 3. So it's kind of like we have x minus 3 with multiplicity 2, right, in the denominator. So that's another way to say this, right, is that the zeros of the polynomial in my denominator are respectively negative 3 with multiplicity 1, negative 2 with multiplicity 1, and positive 3 with multiplicity 2. So there are the factors in my denominator. And so therefore, those are the values that we have to exclude from consideration in my domain. So if I want to know what the domain of my rational function is, I need to take what I just learned about the denominator, and I just learned that the denominator is equal to x plus 3 times x plus 2 times x minus 3, the quantity squared. And I want to find out what values of x make that expression equal to 0. And since I have factored that polynomial, and I have a 0 on the right-hand side, you know the drill, or at least I hope you know the drill, is that we can now give each one of these three factors its own equal to 0 equation, and we have now three very simple equations to solve for x. Solutions are x equals negative 3, x equals negative 2, and x equals positive 3. And this x equals positive 3 has a multiplicity of 2. In case that matters. It does matter in a particular way in a few minutes, but for right now, we just care, if the question is about domain, that these are the three values of x that I have to exclude. And those correspond, on my graph, to exactly those three x values that are missing from my domain. X equals negative 3, apparently from my graph, appears to be this place where the graph has a hole. X equals negative 2 appears to be the place where we have a vertical asymptote. And x equals 3 is a place where we have another vertical asymptote. So So those are the three values that we exclude from the domain of my rational function. Let's go over to the grapher here for just another quick second. So here's my GeoGebra graph of this rational function. Let's turn on the axis numbers just so that we can verify that we're seeing what we expected to see. Show the numbers on the x-axis. And sure enough, x equals -2. Let's sketch that line in here. X equals -2. That's that vertical line that we see right there. I'm going to make it a dashed line here just so that it kind of looks like one of our vertical asymptotes. Same thing with x equals +3. That's this vertical asymptote right there. Make that into a dashed line. And then the other part, the other x value that we're apparently having to exclude according to our work was x equals -3. But when I graph the vertical line, x equals -3, it sure doesn't look like the behavior of my function near that x value is well explained by what's happening at that point, right? It doesn't look like a vertical asymptote in the same way that the other x values that we're looking at, x equals -2 and x equals 3, look like they do explain the behavior of this function if we were to zoom out. But x equals -3, that vertical line doesn't. So what we're seeing here are two different types of local behavior for a rational function. And those different types of local behavior are what we want to look at together next. So near the excluded values of rational functions, there are two different types of local behavior that can happen. There are vertical asymptotes and there are holes or removable discontinuities. And so what we want to understand next is how do we parse near an excluded value of x in the domain. How do we know whether we have a vertical asymptote, and if we do, then what kind of vertical asymptote is it, or whether we have a removable discontinuity, in other words, a hole. So let's take a look at how to classify these different types of local behaviors at my three different excluded x values, -3, -2, and +3. So first, let's start from our factored form as far as we've factored it so far for our rational function, and that's this polynomial and this polynomial. So we factored the denominator to help us find the domain, but we haven't done anything at all with the numerator yet. And that should make you a little bit suspicious because the numerator does have an important role to play in understanding the salient features of a rational function and its graph. So what role does the numerator play in all of this? It's going to help us to classify local behavior, and also it's going to help us to determine the x-intercepts of a rational function. So let's go one piece at a time. Remember, each of these excluded values in my domain corresponds to one of the factors that made up my denominator of my rational function. The x plus 3 factor accounted for the fact that -3 was excluded from my domain, and so there's something interesting, some interesting local behavior near x equals -3. The x plus 2 factor accounts for this interesting behavior near x equals -2. And the x minus 3 squared factor accounts for the interesting behavior near x equals +3. So each of the factors in my denominator gives me interesting local behavior on my graph. So how do we understand what kind of local behavior there is? Before we go any further, let's bite the bullet and factor our numerator. Because in factoring the numerator, we're going to be able to completely understand the role that that numerator plays in classifying these different types of behavior. Again, because this numerator is a 4th degree polynomial, I'm not going to factor this using some technique that we know, other than if we remember synthetic division, we can take some guesses at what the factors are of 24 and try to divide by x minus those factors, and then do quotient remainder of 0, and so on. But whatever technique that you use, if we factor this numerator, it comes out to this set of 4 different factors. I have an x plus 3, I have an x plus 1, I have an x minus 2, and I have an x minus 4. So there's 4 factors in the numerator for this rational function. So let's think about what this now completely factored form of this polynomial is able to tell me. Starting from our first excluded value, x equals -3. When I look at the, sorry, let me zoom in on this a little bit so we can see what's going on as clearly as possible. So when I look at this excluded value at x equals -3, First of all, that excluded value at x equals negative 3 was excluded because my denominator had a factor of x plus 3 in it, right? This factor, x plus 3, becomes 0 at x equals negative 3, and that's why that value is excluded, because that factor is in the denominator, and we cannot divide by 0. Right? So the fact that there was an x plus 3 in the denominator is why we excluded this value. But something that we notice about this is that there is not only a factor of x plus 3 in the denominator, but there is also a factor of x plus 3 in the numerator as well to match it. And that fact, the fact that both my numerator and my denominator had a factor of x plus 3 in it, that allows the problem factor of x plus 3 downstairs. This is the factor that caused us to remove this value from the domain in the first place. That problem factor cancels completely in my expression. And because it can be canceled completely, what that means is that but for the fact that we have to take negative 3 out of the domain of my function, except for x equals negative 3 making my function undefined, my function is otherwise exactly equal to the expression that we get by canceling the x plus 3's. This expression, which is my leftovers. So as long as x is not allowed to equal negative 3, the value of my function everywhere else on the graph is exactly equal to this simpler rational function. And this simpler rational function no longer has a problem with x equals negative 3 in the denominator. And so when we cancel that x plus 3 completely, we completely fix the problem that used to exist at x equals negative 3. That's the behavior that we see when we have in our graph something called a removable discontinuity, or a hole. My graph has a hole at x equals negative 3, because all of the factors of x plus 3 in the denominator that caused the trouble that caused us to remove negative 3 from the domain all cancel completely when we factor both numerator and denominator. So anytime all of our problem factors at an excluded value of x completely cancel, that accounts for a hole, a small gap, a removable discontinuity in the graph of my function. We call it removable because if I were to fill in this hole, I would have no problem at all here in the domain. I would have a continuous piece of graph at that x value. Right? So we can fix that discontinuity in my graph just by filling in that hole, adding a single point onto the graph. So we have a hole in the graph of this function at x equals negative 3. For now, we're not going to actually go into what the y value of that hole is. But let me just mention really quickly, we would find the y value just by plugging x equals negative 3, evaluating this leftover function for x equals negative 3. Because this leftover function now has a well-defined value at x equals negative 3 because the denominator is no longer 0 because that problem factor canceled entirely. So that's how to spot a hole, a removable discontinuity in the graph of a rational function. On the other hand, removable discontinuities are pretty rare. Removable discontinuities are rare because they require all of my denominator factors to cancel completely. What's more common is that my problematic factors do not cancel completely in the denominator. And when that happens, the behavior that we get is called a vertical asymptote. We get a vertical line that explains the behavior of this function as we approach that x value from the left and as we approach that x value from the right. So at least if we believe our graph, both x equals negative 2, this vertical line here, and x equals 3, this vertical line here, are going to be vertical asymptotes for this rational function. How could we know that from the algebra? How do we tell the same kind of story? Let's start with x equals negative 2. And think, how could we have known that x equals negative 2, that excluded value, gives rise to a vertical asymptote? Well, x equals negative 2 is excluded from my domain because x plus 2 is a factor in the denominator, right? Near x equals negative 2, this thing becomes 0. And that gives us a 0 in the denominator, which makes a problem, right? And so my problematic factor at x equals negative 2 is this x plus 2 factor. But there's no counterbalancing x plus 2 factor in the numerator now to cancel it out. And so because the problematic factor does not cancel in this example, that is what explains the fact that we have a vertical asymptote at x equals negative 2. So anytime our problematic factors in the denominator do not completely cancel when we place things into their factored form, we get a vertical asymptote every time. And sure enough, there on our graph is the vertical line x equals negative 2 That is my vertical asymptote at this excluded value. So just knowing that there's a vertical asymptote is only a part of the puzzle. The other part of the puzzle is how do I know what this graph actually does near my vertical asymptote? And what I mean by that is there's a difference, a qualitative difference between this vertical asymptote that we're seeing and this vertical asymptote that we're seeing at x equals 3. At this vertical asymptote, my function on one side of the vertical line approaches positive infinity in its end behavior, so it crashes through the ceiling. But on the other side, my function's graph crashes through the floor as we approach this vertical asymptote. So we get this sort of mixed behavior. It goes to infinity on one side, but it goes to minus infinity on the other side. And so we get this sort of that shape happening at that vertical asymptote. We could also get the opposite happening depending on the circumstances. So we get these two different flavors of infinity that my function approaches near that vertical asymptote. Whereas near my other vertical asymptote that we expect to see at x equals 3, we have agreement that on both sides of that vertical asymptote, my function is crashing through the floor, so f of x is approaching negative infinity from both sides. So how do we do that classification? How do we tell what's happening with the value of a function near one of its vertical asymptotes? Well, for this, we need to take a closer look. The fact that x plus 2 becomes 0 at this value of x is why we have a vertical asymptote in the first place. The second order question, though, is what's happening to the numerator and the denominator on either side of that problematic x value. So to figure this out, we're going to create what I call a sign chart. So near x equals negative 2, I want to know what's my numerator doing. Is it positive or is it negative on the left side of this value and on the right side of this value? Similarly, what's my denominator doing? Is it negative or positive on the left side of this value, on the right side of this value? And if we get that classification down, it'll help us to figure out what this vertical asymptote is doing. So I'll make my sign chart first just by noting that at x equals negative 2, my denominator is equal to 0. That's why this x value was a problem in the first place. What about my numerator? Well, notice that when x is equal to negative 2, every one of the factors in my numerator has a sign that's non-zero. X plus 3 is going to be positive when x is negative 2. But x plus 1, x minus 2, and x minus 4, those are all negative when x equals negative 2. Notice I don't care what the actual numbers are, I just care about the signs. Right? This factor is positive when x is negative 2. These three factors are each negative when x is equal to negative 2. And so when I multiply them together, I get a positive times a negative times a negative times a negative, which, since I had an odd number of negative signs, gives me a negative value. But the other thing that we notice is that that's going to be true even for a value of x that's a little bit larger than negative 2, like negative 1.9 or something like that. All of these factors are still going to have the same sign at x equals negative 1.9 because there's no factor on top that's changing sign at x equals negative 2 because there's no factor of x plus 2 upstairs. And so both on the right side and the left side of x equals negative 2, my numerator, all of its factors remain positive, negative, 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 and so the product of them remains negative. So the beginning of my sign chart is just that my numerator of my rational function is negative, both at and on both sides near x equals negative 2. It's my denominator that's doing something more interesting, because this factor becomes 0 at x equals negative 2. But what about just a little bit to the left, or just a little bit to the right of x equals negative 2? Just a little bit to the left of x equals negative 2, this factor is going to become negative. Just a little bit to the right of x equals negative 2, this factor becomes positive. So this factor here is going from negative on the left to 0, and then to positive on the right of x equals negative 2. Meanwhile, my other factors, my x plus 3 is not changing sign. My x plus 3 is negative on the left, negative here, and negative there. My x minus 3 squared, because it's a square of something, is positive on the left, positive on the right, and positive at x equals negative 2. So this x plus 3 is this x plus 3 for x values that are near negative 2 is positive at just to the left and just to the right of x equals negative 2. This x minus 3 quantity squared is positive just to the left, just to the right, and at x equals negative 2. And so it's just this x plus 2 that's changing from negative to positive to negative to 0 to positive in my sign chart. So if I pick a value of x that's slightly to the left of x equals negative 2, then this factor is positive, this factor is negative, this factor is positive. Plus times plus is going to give me negative. If I pick a value of x that's slightly larger than x equals negative 2, then this factor is still positive, but this factor is now positive, This factor is still positive. Plus times plus times plus gives me plus. So here is my sign chart. Here's what my numerator is doing, near x equals negative 2. Here's what my denominator is doing, near x equals minus 2. So if I want to understand what that means about my vertical asymptote, I just need to look at what I get when I divide numerator by denominator. So as we get closer to x equals negative 2 from the left-hand side, my numerator and my denominator are both negative. And so my value of f of x is going to be a negative number divided by a negative number. And when I divide a negative by a negative, the result is positive. And so as x approaches negative 2 from the left-hand side, f of x is approaching infinity because my denominator is becoming 0, but my numerator is not. But the kind of infinity that it becomes is negative divided by negative, in other words, positive. So when we look back at the graph, how is that reflected? Well, when we approach negative 2 from the left-hand side, in the x direction, in the y direction, my graph is crashing through the ceiling. F of x is approaching positive infinity. What about the story on the other side? As we approach negative 2 from the right-hand side of the x-axis, so as we come in this direction towards x equals negative 2, we're approaching infinity once again because we have a finite number divided by 0, non-zero finite number divided by 0. My numerator is still positive, but through it all, my denominator on this side of x equals negative 2 is positive. And so the kind of infinity that f of x approaches is negative divided by positive. But negative divided by positive is negative. And so f of x is approaching minus infinity at that point. So on our graph, as x approaches negative 2 from the right-hand side, the value of f of x crashes through the floor towards minus infinity. So that's how we use these sign charts to classify what kind of asymptotic behavior we have near a vertical asymptote of the graph of f of x. And so that's how we can tell that in this example, we have a vertical asymptote at x equals negative 2 because my denominator became 0, but my numerator did not, because my problematic factor of x plus 2 does not completely cancel when we do all of our algebra. And using a sign chart, we could tell that on the left side of that vertical asymptote, my function is approaching positive infinity because we had negative numerator and negative denominator. And on the right-hand side of that asymptote, my function crashed through the floor towards negative infinity because we had a negative numerator but a positive denominator. So that classifies the end behavior of this function near x equals negative 2. Now let's go back in and do the same analysis for our other vertical asymptote, x equals 3, the one that we see right here, and that we're kind of expecting, it's behind my head here, we're kind of expecting that the function crashes through the floor on both sides of that vertical asymptote, so f of x goes to negative infinity. Let's see if our intuition is vindicated by the same process that we just applied to get the behavior at the asymptote x equals negative 2. So my factored form is this. My problematic factor at the x value x equals positive 3 is x minus 3 the quantity squared. It doesn't completely cancel, and so we have a vertical asymptote. But at the same time, my numerator at x equals 3 has a sign of positive times positive times positive times negative. So my numerator is negative everywhere at and near x equals 3. So the numerator doesn't change sign right there. It's negative the whole way through. What about my denominator? Well, so x minus 3, the quantity squared, that factor, because it's a square, the perfect square of any real number is non-negative. And it's only 0 when that number is 0. So that number is 0 at x equals 3. But everywhere else, that factor is going to be positive. Positive on the left and positive on the right. Meanwhile, x plus 2 for these x values is also positive, both on the slightly to the right of x equals 3 and slightly to the left. X plus 3 is also positive, slightly to the right and slightly to the left. So all three of those factors are positive, and so when I multiply them together, I get positive every single time. So when I do the sign chart at this asymptote, I find out that on the left side of this vertical asymptote, my rational function looks like something which is a negative number on the numerator divided by a positive number in the denominator, minus divided by plus. But that the same is also true on the right side of my asymptote. So at the end of the story for that particular vertical asymptote, we end up with a division, negative over positive, both on the left and on the right, which means that f of x approaches negative infinity both on the left side of this vertical asymptote, as we see right here, but also on the right side of this vertical asymptote, as we see happening right there. This is easily the most challenging thing that we will need to do with rational functions, is classify their local behavior. What gives me vertical asymptotes? What gives me removable discontinuities or holes? And for those that do give me vertical asymptotes, what kind of local behavior are we seeing at that vertical asymptote? Are we going to plus infinity, or are we going to minus infinity on both the left side and on the right side? And using a sign chart is the way that we can make sense of that whole process. So that covers most of the cases that we're going to be interested in this semester. We now know how to classify the domain of a rational function by looking for its excluded values, by finding those values of x that make the denominator equal to 0. We also know now how to discover which gaps in the domain, which excluded values give rise to holes in the graph, removable discontinuities. Those are ones in which the problematic factor in the denominator completely cancels with counterbalancing factors in the numerator, right? So that was like my example at x equals -3. And how to discover which of the excluded values from the domain give rise to vertical asymptotes. And those are going to be the ones where the problematic factors in the denominator cannot be completely canceled by counterbalancing factors in the numerator, which is generically the case. It's sort of lucky when we get cancellation. When we don't get that cancellation, we get vertical asymptotes. And using a sign chart can tell us what the behavior looks like near those vertical asymptotes. So I want to wrap up our live stream today with another oddball example of something that doesn't always happen. In fact, most of the time it doesn't. But we want to understand also one last type of end behavior. So when we talked about end behavior at the beginning of the live stream today, we really only talked about it in terms of horizontal asymptotes and also end behavior that crashes to plus and minus infinity, which looks like a polynomial of a positive degree. Well, there's one other type of asymptote that we occasionally will run into in calculus and in pre-calculus, and that is an asymptote in which the behavior of the function looks like a line as x goes out to plus or minus infinity, but the line that it looks like is not a horizontal line. We call those asymptotes slant asymptotes. So let's build an example of a graph that actually is going to do this. So I'm just going to type it in here into my GeoGebra grapher. F of x equals, I'm just going to make one up here. How about 2x squared minus 11x plus 1, or something like that. Plus 3, I don't know, it doesn't really matter. And then I'm going to divide that by 4x. No, I'll just divide it by x plus 4, or something like that. So here is a rational function sketched on my GeoGebra grapher right here. And in this default viewing window, we're not really seeing a whole lot of interesting behavior. It kind of just looks like almost like a quadratic. It looks like a parabola kind of, right? It goes down and then it comes back up. But if I want to understand the end behavior of a rational function, as with any function, what I want to do is I want to start zooming out. And the more that I zoom out, the more that I'm going to get clues to its actual end behavior. So keep zooming, keep zooming, keep zooming, keep zooming. So we have to zoom out pretty far, but eventually we see that there's more to this story, right? There's another piece of this function that we didn't see in the beginning. I'm going to keep zooming out. I'm actually going to turn off my axes for a second. Zoom out, zoom out, zoom out, zoom out, zoom out. So the more that I zoom out, there's sort of two features of the graph that are becoming apparent. One feature is this vertical line that I'm seeing right there. That vertical line looks as though it ought to correspond to some vertical asymptote for my function. And indeed, according to what we've been saying in today's live stream, this x plus 4 in the denominator is a giveaway, right? As soon as that quantity becomes 0, in other words, when x is equal to -4, we should get a vertical asymptote. And we can do a sign chart to discover that the behavior near that vertical asymptote is that the function goes to positive infinity on the right side and negative infinity on the left side of that vertical asymptote. So that accounts for the vertical line. But notice that we're seeing another line here as well, this diagonal line. What in the world is that diagonal line doing? So that diagonal line, as you might expect from the title of this last segment of our live stream today, that diagonal line is what we're going to call a slant asymptote for our rational function. So a slant asymptote is a line that is not a horizontal line that explains the end behavior of a rational function. So how can we figure out what that slant asymptote actually is? To figure first of all, let's ask the question: when do we know that there is a slant asymptote for a rational function? Let's write out. I'm going to write it on my whiteboard here real quickly, which you can't see, but I'll show it to you in just a moment. I'm going to write out the formula for my f of x. It's 2x squared minus 11x plus 3 divided by x plus 4. So there is the formula for my rational function. And I want to ask the question, why should we expect that this function has a slant asymptote? Well, here is the key to unveiling slant asymptotes for a rational function. The key is to re-express your rational function using polynomial division. Express it as a quotient and a remainder. This is one of the reasons why we developed this topic of polynomial division in the first place. So if I apply polynomial division to this, let me do it in long division format. I'm going to take my denominator, x plus 4. I'm going to divide it into my numerator, 2x squared minus 11x plus 3. And when I carry out this polynomial division, my x goes into 2x squared 2x times. And then I multiply. 2x times x plus 4 is 2x squared plus 8x. And then I'll subtract. My 2x squareds go away. A negative 11 minus 8 is going to give me negative 19x. Then when I do this division, x goes into negative 19x, exactly negative 19 times as the quotient. And then when I multiply that negative 19 by x plus 4, I get negative 19x minus 19 times 4, that's 76. And then I'll carry out the subtraction of 3 minus negative 76, and I will get 3 plus 76, right? So 79. And so that becomes my remainder. And so at the end of this polynomial division process, what we find out is that we can re-express this polynomial as the sum of a quotient and a remainder. I'm going to write this just right up here at the top. The quotient that we get from this process is 2x minus 19. And the remainder that we get out of this process was 79. And so when we express that remainder, that 79 is 79 on top of my divisor, x plus 4. So we have these two pieces in my rational expression. We have the quotient piece, 2x minus 19. Whoops, that's a bit hard to read. Let me dim that a little bit. So we have the quotient, 2x minus 19. And then we also have this remainder, 79 over x plus 4. So let's hang on to that quotient and that remainder. Let's go back into our grapher and see if we can make sense about what that quotient and that remainder are actually telling us about the graph of this function. So let's graph my quotient. I'm going to call it q of x. That was, we decided, 2x minus 19. Okay. So that is the graph of a line, right? It follows y equals mx plus b, where m, the slope, is 2, b, the y-intercept, is negative 19. And its graph is this red line that we're seeing over here. If I zoom out, it sure looks like that quotient is the diagonal line to which my rational function approaches as x goes out to plus and minus infinity. So that quotient is the equation of my slant asymptote. It's the formula that defines the slant asymptote for my function. So y equals 2x minus 19 is my slant asymptote. So polynomial division is how we discover an equation for a slant asymptote for a rational function. Right? And we discover it by doing the division and finding the quotient. The quotient here is the 2x minus 19. And when we look at the graph, y equals 2x minus 19 is exactly this diagonal line to which my graph asymptotes as we get out towards plus and minus infinity. So what is the role of the 79 over x plus 4? Well, the 79 over x plus 4, my remainder over here. That 79 over x plus 4's job is just to tell me the difference between the slant asymptote and my original function. So that 79 over x plus 4 just kind of tells me how far from the slant asymptote that my rational function is. How far away from the asymptote my rational function is, right? And what you notice about it is it has a vertical asymptote at x equals -4. Right? So this kind of accounts for all of my rational function-like behavior. This piece accounts for the linear function-like behavior that we're seeing in this rational function. So the last question is, how would I have known that this indeed has a slant asymptote in the first place? Why should it not have been surprising that this function has a slant asymptote? And the reason for it is that when we did the polynomial division, we ended up getting a quotient whose degree was 1. Our quotient was a linear polynomial. But our quotient was linear exactly because we were dividing a polynomial of degree 2 by a polynomial of degree 1. My numerator had a degree 1 higher than my denominator did. And there's the general principle that we'll take to the bank on slant asymptotes. Slant asymptotes are a thing exactly when the numerator degree is 1 higher than the denominator degree. So in this case, the numerator degree was 1, the numerator degree was 2, the denominator degree was 1, so the numerator was 1 higher than the denominator, degree-wise. And so that's why we had a slant asymptote in this example. So just to recap, this rational function has a slant asymptote. So f has a slant asymptote because its numerator has degree 2, which is 1 larger than the denominator. That's the first observation. And the second observation is that the slant asymptote, we can find the equation of the slant asymptote just by finding the quotient when the numerator is divided by the denominator. You can't read all of that, but you got what I just said, hopefully. So what I'm hoping is that today's live stream was a good survey of all of the interesting behavior that rational functions may have. So we talked about, first of all, what can we do with a rational function without factoring it, without finding its factored form? The answer is not much, but we can find the end behavior of a rational function without having to factor it and discover its factored form. That's really good news, because factoring is, in general, kind of really bad news. So if we come back to the example that we started with one last time here, we were able to discover the end behavior of this rational function by just looking at its leading coefficients, its leading terms, right? We just took and scratched out everything but the x to the fourths, discovered that as we divide those, we get the number 1 as x goes to infinity, and that accounted for the horizontal asymptote that was part of the end behavior of this rational function. But for different rational functions, if the degrees of their numerators and denominators are not equal, as they were in this example, we can either get a case where the horizontal asymptote is 0, or a case where we have no horizontal asymptote at all and have different type of end behavior. So that's what we were able to discover without needing to factor. But any other question about local behavior of rational functions, we need the factored form really as the most efficient way to understand it. We need to factor to discover the domain of a rational function by discovering the excluded values of x that make the denominator equal to 0. Factor your denominator, set that factored form equal to 0, and you find out which values you need to exclude from the domain of our function. And then once we know which values that we need to exclude, it's then a matter of actually excluding them and figuring out what the local behavior near those values is. So near x equals -3 in this example, we had a type of behavior that is called a removal discontinuity, or a hole, because that problematic factor of x plus 3 cancels completely. And so we end up with this hole instead of a vertical asymptote. But the other two excluded values, x equals -2 and x equals +3, both gave us vertical asymptotes because the problematic factors did not completely cancel. And when that happens, we can use a sign chart to discover the local behavior near that vertical asymptote. In the case of x equals -2, our function went to positive infinity on the left side and negative infinity on the right side, based on the signs of the numerator and the denominator near that point. Near x equals +3 at that vertical asymptote, we had agreement that both on the left and the right side of the vertical asymptote, my function crashed through the floor, going toward negative infinity. And then finally, we also looked at how to discover slant asymptotes. Slant asymptotes occur whenever the degree of the numerator is 1 higher than the degree of the denominator, and we can find the equation of the slant asymptote by finding the quotient that we get from polynomial division. So that's the story for rational functions. In our next live stream that we're going to do tomorrow, we're going to take that last step forward into our last function type, which is the exponential functions. You won't want to miss that because it gives us a lot of power to model different types of real-world scenarios that we encounter in our everyday lives and in our jobs. So I hope to see you there for our next live stream tomorrow.